Okay, so let's start going through the solutions. We'll start, of course, with the short questions. And question 1 is a 30-mark question. Some students will absolutely love this question and others will move right past it, saying it's an old-fashioned complex numbers question using the Moivre's theorem. So some students will say, yep, I know exactly what to do here. And others will be saying, I'm definitely moving on. So the first one says we're told that z is equal to minus 8 plus 8 times the square root of 3i. Find the modulus of z and show that the argument of z is 2 pi over 3. So in this case, we're directed to show that the argument is 2 pi over 3, the angle. So of course, straight away we know we're talking about radian measure. So the very first step, of course, is to plot the point on the arcgan diagram. So, for everyone, that's going to be your starting point. So our point again is minus 8. So negative 8 units along the x-axis plus 8 root 3i. So 8 root 3 up on the imaginary axis. So we can figure out, and we're going to work with our angle first. Of course, what we're looking for is our argument, our degree of rotation anti-clockwise from the positive sense of the real axis. But we're going to start off first by finding alpha, our reference angle. We do that because we can form the right angle triangle. We know that 8 root 3 is going to be the opposite. And we know that 8 is going to be the adjacent. So we use the tan of alpha because the tan of alpha is the opposite over the adjacent. So 8 root 3 over 8. Of course, that will simplify down to root 3. So I'm going to get the inverse tan of root 3. So alpha is going to be equal to the inverse tan of root 3. And the inverse tan of root 3 in radian measure is pi over 3. It's 60 degrees. But we're going to be dealing with radians here, so it's going to be pi over 3. But of course, what we're looking for is theta. And in this case, theta is going to be, we know of a kind of a rotation, a straight line rotation would be 180 degrees or pi radians. So how am I going to calculate theta? Well, theta is going to be equal to pi radians minus pi over 3, the reference angle. So pi minus pi over 3 is going to give me 2 pi over 3. And 2 pi over 3 is 120 degrees because, of course, alpha would be 60 degrees. And if I took 60 from 180, I get 120. But I was asked for it in radian measure, so I will definitely have to give it in that form. I will then calculate the modulus, the length, the distance of the point minus 8 plus 8 root 3i to the origin. So it's Pythagoras' theorem, really, although some people think of it as the square root of the real part squared plus the imaginary part squared. But it's the same as the hypotenuse is equal to the square root of the sum of the square of the other two sides. So we get the square root of 256, we get 16. And that was worth 10 marks. So relatively straightforward 10 marks for those who have practiced it. Just knowing, of course, we do have to get the argument in terms of in radian measure. Okay, so then we were asked to use de Moivre's theorem, and it's asked us to find z cubed, giving your answer in the simplest form. So on page 20 of our table books, we find de Moivre's theorem, and it says to us that we know that if we have a complex number in polar form, in the form of r cos theta plus I sine theta to the power of n, well, that can be written as r to the power of n times cos n theta plus I sine n theta. What we say is the modulus r gets raised to the power of n, the argument theta gets multiplied by n. So we can do this in either degrees or radians, because we're just going to have to get our answer in the simplest form. It hasn't directed us to continue on in radians. So I can say z is equal to 16 times cos of 120 plus I sine of 120. So z to the power of 3, well, I should have a square bracket here because it's all raised to the power of 3. The 16 times cos 120 plus I sine 120 would be raised to the power of 3. We're going to use de Moivre's theorem. And as I said, the modulus, which is 16, would be raised to the power of 3. And the argument, which is the 120, would be getting multiplied by 3. So in this case, 16 to the power of 3 would be equal to 4096. 120 times 3 would be cos of 320. 320, where am I getting that from? 360. So we're going to have the cos of 360 plus I sine of 360. Of course, we know that the cos of 360 is going to be equal to 1, and the sine of 360 is going to be equal to 0. So when I multiply through my 4096, I'm going to get 4096 plus 0i. You do have to keep your 0i in there because you want your answer to be of the form in the form of a plus bi. Okay, so that will be my answer to that question. Now you could have done it, of course, in radians, and you will see in the marking scheme that we've included the two versions of it. And what you would have, of course, is this will be the 2 pi over 3, 2 pi over 3, and you'd have the 2 pi over 3 for your angle in both cases, and you'd be multiplying by 3. So on this line here, you would have the 4096, 2 pi over 3 times 3 will just give you 2 pi. So it'd be the cosine of 2 pi plus I sine of 2 pi. But of course, for the same reason, it brings you back to the exact same point on the argand diagram. So 2 pi is a full rotation. So the cos of 0 will be 1, and the cos of 2 pi would be 1, and the sine of 2 pi would be 0. So again, multiplying in, you're going to get 4096 plus 0i for 10 marks. So that's the simplification, and that's your answer. Sometimes students will get confused between that and the solving, but in this case, because we're going to be asked to find the values, plural, of w, such that w to the power of 4 is equal to z, and it asks you to give the answer in the form of a plus ib. Well, in this case, of course, we hopefully can identify here that we're going to solve, because we're starting off with z to or w to the power of 4, but we want to find the values of w. So what we do in this case is we say, okay, we know what z is. So we know that z is equal to 16 times cos of 2 pi over 3 plus I sine 2 pi over 3. I'm going to continue on here this part in radians. I know some students will find this to be the more difficult one, so I'll do this in radians, but you'll see in the marking scheme it's done in degrees as well. So we're going to apply de Moivre's theorem here in another way. Basically, I'm going to get the fourth root of both sides. The reason I'm going to do that is so that I get w to the power of 1, w on its own. So I'm going to get the fourth root of one side. What I do to the left, I do to the right. So that gives me 16 times cos 2 pi over 3 plus I sine 2 pi over 3 to the power of a quarter. I'm going to firstly get my general form. So again, one difference between using de Moivre's theorem to solve and using de Moivre's theorem to simplify is when you're solving and finding more than one answer, you must get the general form. And so the general form involves adding 360 times n, a full rotation around the circle of 360, or a full rotation, if you want to do it in radian measures, of 2 pi times n. So 2 pi is the same as 360. So I'm going to be adding on my 2 pi times n. So now my general form is going to be my 2 pi over 3 plus my 2 pi n. both in the cos and in the sine. I'm going to apply my de Moivre's theorem. The modulus gets raised to the power of 1/4. And the argument, as you see, the angle is going to be multiplied by the quarter. So I'm going to have, okay, my 16 to the power of 1/4 is going to be 2. And when I multiply the argument by 1/4, 1/4 times 2 pi over 3, 1/4 times 2 pi over 3 will give me 2 pi over 12. 1/4 times my 2n pi will give me n pi over 2. Same here, when I multiply my quarter into the bracket here, 1/4 times 2 pi over 3 will give me 2 pi over 12. 1/4 times 2n pi will give me pi n over 2. So we've done a lot of the hard work now, just a little bit left to go. We know we need values, so we're going to have to find more than one. What we're going to do is we're going to sub in different values for n, and we're going to get different answers. Those of you who've done it a number of times know we're going to have 4 distinct answers because the power is 4. So we start off with the easiest one, which is n equals 0. So if I put in n equals 0, we can see we've tied it up here a little bit, but when we put in n equals 0, I'm going to have, 0 times pi over 2, that'll be 0 in both of these brackets. So I get 2 times cos pi over 6 plus I sine pi over 6. So I'm going to get 2 times root 3 over 2 plus I times a half. I'm going to multiply my 2 through the bracket, and I'm going to get root 3 plus I. So that's one of my solutions to this equation, w to the power 4 equals z. And I got that by putting n equals 0. If I go for n equals 1, in this case, of course, I'm going to have pi over 6 plus 1 times pi over 2. So it'll be pi over 6 plus pi over 2. That ends up being 2 pi over 3. Same for the cos and the sine. So I get cos of 2 pi over 3, that's minus a half. Sine 2 pi over 3, that's root 3 over 2. I'm going to multiply my 2 through the bracket, and I get minus 1 plus I times the square root of 3. So you can see a similarity between the two answers, but obviously not exactly the same. So you would know there's a little connection between the two. We'll see it at the end. We put in n equals 2. So now we're subbing in n equals 2. So we end up with 2 times cos 7 pi over 6 plus I times 7 pi over 6. Type it into the calculator, you get minus root 3 over 2 for the cos and minus a half for the sine. We multiply 2 through by the 2 and we get minus the square root of 3 minus 1 I. And then when n equals 3, we end up with 2 times cos 10 pi over 6 plus I sine of 10 pi over 6. 2 times a half minus I times root 3 over 2. 1 minus I times root 3. Some of those answers might look like they're the ones we had earlier, but they're all different from each other. There are 4 different answers. You might say, okay, how do we know to stop at w equals 3? We had 0, 1, 2, 3. Well, if you put in w equals or n equals 4, you would find that you would get the same answer that you got for n equals 0. If I plot my answers, I just had to list them, but if I actually plot them, so here are my 4 answers. As I said, they kind of look similar to each other, but they are different. But if you plot them, you will find that there is a connection between them. And basically, they're all the same distance, of course, from the origin. And if you multiply the W0, if you multiply that by I, you will get W1. If you multiply W1 by I, you get W2. If you multiply W2 by I, you're going to get W3. Each is an anti-clockwise rotation of 90 degrees relative to the first one. So that was my the final part of this, it was 10 marks. As I said, some students would really like that, be right up their street, and other students would find that to be very difficult, and they would be hoping that question 2 would be a one that would suit them more so.